Alright, hello and welcome. This is the next topic of X in C3. This is called Exponentials. Oh, sorry. In this video, I'm just going to be capping on what an exponential function is, how we calculate the exponential function, and the inverse of the exponential function, what that is, and then we'll be doing a few questions about it, and just generally a few hints and tips of what to do. Just double checking there's nothing else. Yep. So we'll just be talking about exponentials, the inverse of an exponential, and then what that shows us. Okay, so what is an exponential? What does an exponential graph look like? Okay, so an exponential is something that looks like y equals a to the power x. And you go, what is this e? Okay, well then e is, so if you've got your calculator, just bring it up here. So this is just a standard scientific calculator. If you go and shift on this one, and it's that little, I don't know if you can quite see it, but above the in, which is the inverse of the exponential by the way, you get a little e there. And if we type in 1, which is just the power of its 1, we get the 2.71828, as you can see. So that's what the exponential is. And the exponential graph looks something like this. And you're going to ask me, how do I know this? And this little point here is 0, 1. Now, how do I know that? Well, anything to the power of 0 is 1, and because that is y of e to the power x, x is 0, e to the power 0 is 1. That's why it goes like that. And obviously we can do our standard thing for this of translations, reflections, different variations on the subject, so that you could class that as fx. And if we cast our minds back to C1, we talked about stuff like f of 3x, so that would be the same as putting y equals e to the power 3x, and all we'd do in that situation, it would still be 0, go through 1, but it would be more like that, so that would be y equals e to the power 3x, sorry. And we just use our standard, that's y equals e to the power x. We just use our standard C1 transformations of graphs in that explanation. Okay, so that's what an exponential function is. Now, what does this mean? Say if we want to find x here, and we've got 10 equals e to the power x. How do we work that out? Well, we can't use logs, because this isn't a function. What we do is we do the inverse of e to the power x, which the inverse of e to the power x is ln, which is that bottom I was talking about before. 10 equals, so if we do the inverse of this, we get that equal to x, that equals x, and then that x could equal whatever that is. So if we do the ln of 10, the in is what I call it, and that gets us 2.30, and it goes on. So if we did, so to prove that works, so essentially what I did was I did that on my calculator, the ln of 10, which e to the power x equals 10. So I did the the ln of 10. Now that gave us a number of 2.3 whatever it was. So if we go now, so that's the x up there. So if we just went to the exponential function, the e, and we put that 2.300, so this is going to come up to the same sort of thing. If I'd have typed that in properly, them last few digits, that would have come to 10. So that proves how we can find the value of x there. We can also do it by doing the logarithmic function, which is the similar sort of thing. which I'll explain in a minute when we get into the later part of this topic. So hopefully that sort of told you a bit about graphing exponentials and how to find the powers of exponentials. Generally, the form of an exponential will take the form y equals a to the times e to the power x, which is exactly the same as this, just in this case obviously a is equal to 1, so we don't need to put it, so that's irrelevant, but it does equal that there. That is the same thing, these two are the same, just that one there is a, but we're just assuming we don't need to know that, because we can just imagine it in our heads. Okay, so hopefully that's been a little bit of use to you. And if you're coming up with an equation here, so generally what exponentials are used for, if you're doing physics, is exponential rates and changes of decay or growth. Now generally what this will mean is y, so it could be, let's come up with a sort of a sciencey thing, should know some bit of physicist. So if you've got a say bacteria, okay, it's not really physics but more like biology. If you've got a bacterium and it multiplies, and you need to know the rate at which it's multiplying, what you do is, say this is the number of molecules or number of bacterium. Bacterium, remember, is the plural for bacteria. Bacterium. Said that the right way around. Is the start number. Obviously, the bacterium is going to be different for different things, so it could be the end result, and then the A is what you start with, so that it links to your A, and then your e to the power x, so you times the e, and then x, this x bit here is your rate of change. Now, that's what it says in my book, okay, but very careful with this, because the differential of e to the power x is the rate of change. So it's not actually, even though I've said that, I'm going to rub that out. If you differentiate e to the power x, I'll talk about that in a minute, but that gets you the rate of change, whereas e to the power x is just generally like the rate it increases per second. So it might be, instead of e to the power x, that was just an exponential function, it could be e to the power 1.2 t. So that means starting number times exponential to the power of 1.2 times whatever the time is. And obviously it might not be 1.2 times t, it might be 2.4 times t or 1 plus 2t. But you get the idea. Generally what it is y equals a, you start number times your exponential function to the power of the time if it's a rate of, if it's a bacterium question or something changing. Generally it'll be t, and you always put the t in the power bit of the exponential function. Hopefully that makes some kind of sense to you. Or if the car's increasing in value, it'll be something like that. Okay, so hopefully that's the same for you. One thing I just want to mention, so hopefully we've got that. So I'll leave the exponential function up there. Now I did talk about the rate of change just then, and we know the gradient is the rate of change, so dy by dx. So what do you reckon well actually, you know, if you watch this for the first time, the rate of change, the differential of e to the x is simply e to the x. Now I've done a slight calculation behind that. I've not just simply rewrote the equation. E to the power x, what I've essentially done is it's y equals ex, so it's 1 times e to the power x, and then what I've done is, so it's y equals 1 to the 1 times e to the power of 1 times x, and then what I've done is I've done 1 times 1 and left the 1 times x on top. So basically, to you and I, it'd be dy dx equals 1 times 1 e to the power of 1x. See, I've kept the same power and I've times it by that. Right? If that doesn't make sense, I'll do it again, but with different numbers. So, say our equation is y equals 2 to the power 2x, 2 to the power 3x, and our differential, dy dx, would be 3 times 2, which is 6, so it would be 6 to the power, 6 times the exponential to the 3x. We don't reduce the 3. You don't reduce the 3 to 1. It's quite confusing because that's what you'd normally do in a differential part of the equation. But that's essentially what you do for the rate of change. So if we wanted to know the rate of change, instead of changing, if we changed x to t, we just put the t in there. So let me give you a real example of this. So how long are we doing for time? Okay, so say we were told the starting rate, the starting number, we'll go to the bacterium again. So the start number of bacterium equals 1,500 cells of bacterium. Sorry, I just like using bacterium because I'm a bit of a scientist. So the start is 1,500 bacterium, and we are told the rate of change is 1. It doesn't necessarily have to be in. Sorry. Sorry, I just want to, because there's I was trying to use the example off here without being too obvious. Yeah. Okay. I'll use this. So it says aggressive growth rate of 37% per day. So growth rate equals 37% per day. And it says write down a formula for the number of bacterium present at total time t equals 5 days. So what we're saying here is the number of bacterium, because that's what we want to find out, equals our start of 1,500 bacterium times 1 point. Now it's not times 37 and it's not times e, because e to the power x, that's just the standard exponential function, but we can adapt it to suit. So times 1.37, because that's our rate of change over 5 days. So as I was saying, the times to the power, 5, because it's been 5 days. Now the formula would be not 5, but it would be t, because what we're putting in there is simply the number of days. So it's 1,500 times 1.37 to the power t. That's the equation. Generally, it'd be only e to the power t if it told you that in the question. But if it's asked you to write a formula, that is what you'd write, because that is an exponential graph, because it's to the power of some 1.5 times 10 to the 3. Sorry, that's how I'd imagine it. 1,500 times 1.37 to the power t. That is an exponential. It's going to look something like our equation up there. So it's an exponential. So if we were asked to find it over 5 days, we just change a t to 5, and then whatever that would come to. So if you want to work that out on your calculator, before I do, so 1,500 times 1.37 to the power 5, and that gets you, if I put that in standard form, 7.245 4 times 10 to the 3. Now, bacterium. Now the thing is, you have got to apply it a case in point, right? So this case is talking about the bacterium, okay? So you can't have 0.24 of a bacterium. Obviously it's not 7.24 of a bacterium, it's, you know, 7,000 or whatever. But you need to make sure you've got it to the smallest amount. So you round it down if it's, even if it's 0.8, because you can't add another 0.2 of a bacterium on. You always round it down because it hasn't fully completed that cycle there. So that's essentially what it is. I think I've covered most of the things on there, so just checking timing. I will do a question, so sort of I'll go through a few past paper questions on this topic just in the next video, purely because my camera's about to run out of film, or digital film or whatever, so I just need to give it a bit of a break and put it on my computer. So I'll see you in the next video, and I'll link this the next video into this as a part 2, but we'll see you in the next video. I didn't want to start anything just yet, purely because this is quite a good time to stop. Okay, so thanks for watching so far. Hope you've got that. Any comments, just queries, just post it on the video, and we'll see you in the next one.